In section 3.6, we are going to be looking at something called implicit differentiation. So far, we have been doing what we would call explicit differentiation. In other words, if I look at this function here, f of x equals 2x squared plus 16, this function is explicitly solved for y. So we have y equals, because f of x and y are the same thing, we have y equals, we have y by itself equals, and then we have a function that only has the variable x in it. So it is a function of x. Implicit differentiation allows us to actually take a derivative of an equation if we are not explicitly solved for y. So for example here, this equation is not solved for y. Y is mixed in, not written as a function, but it's just written as the variable y, and it is mixed in with the variable x. So we're going to use implicit differentiation to find the slope with respect to y, so the change in y with respect to x, if the equation is not explicitly solved for y. In other words, if y is not already by itself on one side. Let's review a little bit of notation before we start. Remember that d dx is the derivative of a function with respect to x. If you were to write the derivative of x with respect to x, then anything, of course, divided by itself is 1. And what we've usually been writing is the derivative of y, or the derivative of the function, with respect to x. In other words, we looked at the change in y divided by the change in x, and of course, that is the slope, or the slope formula. So the key in this section is to remember that y, while not written as such, y is considered to be a function of x. So y and f of x really represent exactly the same thing. So when we go to use implicit differentiation, we are actually going to be using the chain rule. So we're going to look through kind of a progression here to see why it makes sense that we would use this chain rule. So if we're taking the derivative, let's say, of y squared, we said y and f of x are really the same thing. So what we're really taking the derivative of is the derivative of the function f of x that's being squared. And we said if we have a function or a group of terms that's raised to a power, then we would use the chain rule to take the derivative. So we would bring the power down to the front, we would write the inside function as is, and then we would write the derivative of the inside function. And since we do not know what the derivative of the inside function is, because we don't know what y is, so we do not know what y is, so we do not know what the derivative is, so we just write it as the derivative of y, whatever that would be, with respect to x. So we symbolically represent the derivative of the inside function by writing dy dx, the derivative of y with respect to x. So this represents, in other words, the derivative of the inside function that we do not know exactly what that inside function is. So that's what we're going to represent as the derivative of that inside function. Okay, so here's a problem and some steps side by side. First of all, we're looking at example 1. We're looking to find the derivative of, we have 2x squared plus y squared equals 16. We're looking to find the derivative of y with respect to x. First thing we're going to do is we're going to differentiate both sides of the equation with respect to x. So we're going to look at each term separately, and we're going to use the same rules that we've been using all along. So 2x squared. The derivative of that, of course, using our power rule, would be 4x. And now we have y squared. So we're going to think about this, remember, as represented as some function of y, so some function squared. Since we have a function raised to a power, we're going to think about using that chain rule. So we're going to bring the 2 out to the front. We're going to write down the inside function, which is f of x, which is the same thing as for us y. Then we're going to write the derivative. We're going to multiply that by the derivative of the inside function. We don't know what the inside function is, so we can't actually write out the actual derivative of the inside function. So as a placeholder, we're going to use dy dx. And then equals, and then we're going to take the derivative also of the right side of our equation, and the derivative of a constant is just 0, so we get equals 0. Next thing we want to do is we want to explicitly solve for dy dx. In other words, we want to get dy dx by itself on one side. So we're going to solve this equation. We have two separate terms, and we want to solve for dy dx. In other words, we want to get this by itself. So the first thing we're going to do is we're going to move over any terms that do not contain dy dx. So I'm going to subtract negative 4x from both sides of the equation. So we have 2y times dy dx equals negative 4x. All right, and then the next thing we're going to do is we're going to get rid of anything that's not dy dx. So within this term, we see we have 2 times y times dy dx. So those three factors are separated by multiplication. So we're going to get rid of the 2 and the y by dividing both sides by 2y. So the 2's cancel, the y's cancel, and we're left with dy dx, so the derivative of the function with respect to x, which is what we were looking for all along, would be minus 4x divided by 2y. And this is the derivative, which we said was the slope formula for any point, and that would represent the x value and the y value of the point. So if we know the x value and the y value of the point, then we can plug that x and y value into the derivative and actually solve for the slope at that particular point. Okay, let's look at another example. So we're asked to find the derivative dy dx by implicit differentiation. So let's go through first and take the derivative of each term on both sides of the equation. So this is just x cubed, so the derivative of that would be 3x squared. And here we have a function raised to a power, so this is the chain rule. So we're going to bring that power out to the front. We're going to write the inside function as is, then we're going to reduce the power by 1. And we're going to multiply by the derivative of the inside function. We said we do not know what the inside function is, so we can't take the derivative of it, so we're going to represent it symbolically as dy dx. Now the third term, we're going to do the same thing. That's just y. So we're going to think about, well, if the function is f of x, what is the derivative of that? It's not raised to a higher power, so we don't have to use that chain rule. Well, of course, the derivative of y would be the derivative of f of x. Well, that would just be dy dx. So the derivative of that with respect to x would, of course, be just dy dx. It's not raised to a higher power, so we don't have to use that chain rule. And now the derivative of the constant minus 4, of course, would just be 0. So we're not going to write that. And then the derivative on the other side of the equal sign, that's also a constant, so that also would be 0. So the next step would be for us to solve for dy dx. Now this time we have two terms that have dy dx. So I have dy dx in one term, and then we also have dy dx in this term. So we want to get rid of any term, first of all, that does not contain dy dx, and we want to move that to the other side of the equal sign. So we're going to subtract 3x squared from both sides of the equation. And we want to solve for only one dy dx. We don't want to have two dy dx's floating around in our equation. So the next step that we're going to do is we're going to factor out dy dx. So think about this as kind of like an implied 1 there. For both of these terms, we can factor out that common factor of dy dx, and we have left over from the first term 3y squared plus, and of course if we factor out everything from this, then we're left with just that placeholder of 1. And then the last thing that we want to do, since we only have one dy dx now on the left hand side, we want to get rid of anything or divide by 3y squared plus 1. We want to get rid of anything that is not dy dx. And we want to do the same thing to both sides of the equation. So now this cancels and we're left with dy dx is equal to negative 3x squared divided by 3y squared plus 1. Now in example 3 it gets a little bit more interesting as far as the solving for dy dx. So let's look inside here. X squared, so we're looking to find the derivative here of x squared. Well, that of course would just be 2x. Now we're looking inside of this particular term. We notice that we have variable x and then we have it multiplied times the function y. So this is going to be the product rule. So let's think about it as two separate functions here. We're going to think about this as 2x for the first function, and that second function we're going to think about as y. I'm going to bring down the minus sign and we'll distribute it after we find the derivative of 2xy. So 2x, so we're going to use a product rule, so it's the first times the derivative of the second. Well, it's just y. And the derivative of y, of course, would just be dy dx. Plus, then it's the second, so that's y, times the derivative of the first, which for here would be just times 2. Equals, and of course on the other side of the equal sign we have a constant which is 6, and so the derivative of that would just be 0. Okay, so it gets a little bit more interesting here because we have two functions multiplied together and we have to use the product rule in order to find that derivative. Now we're going to simplify a little bit. So we have 2x minus, let's go ahead and distribute that negative into both of those terms. So it's minus 2x times dy dx. And then negative gets distributed to this term, so let's say that's negative. Let's go ahead and write the 2 out front, so that's negative 2y, and then that equals 0. We want to solve for dy dx. We want to get this by itself on one side. So the first step to solving for dy dx is to move everything, any term that does not have a dy dx, to the other side of the equation. So we're going to subtract 2x and we're going to add 2y to both sides of the equation. So now we have negative 2x dy dx is equal to, so these terms are going to cancel. We're left with negative 2x plus 2y. Then the last thing we want to do is divide by anything that is not dy dx. So we're going to divide both sides by negative 2x. So our final answer, dy dx, the derivative of y with respect to x, that slope formula would be minus 2x plus 2y divided by negative 2x. For example 4, we're asked to go a little bit further. It asks to find the slope and the equation of the tangent line to the graph of the given equation. So we have 4x squared plus 9y squared equals 36, and we are given the point 0, 2. So the first thing, if we're asked to find a slope, we want to take the derivative. Since we're not explicitly solved for y, then we will need to use implicit differentiation to find that slope formula. So let's look at the first term, that's 4x squared. The derivative of that, of course, just using the power rule, would be 8x. Now for the next term, we're going to use that chain rule. So we have the function y raised to a higher power. So we're going to multiply that power times the front of the function. We're going to reduce that power by 1, and then we're going to multiply by the derivative of the inside function. Of course, the derivative of y is just dy dx. Equals, and so we have equals 36. So 36, of course, the derivative of that would be 0. Okay, we're going to solve for dy dx. So we want to get dy dx by itself. So the first step to doing that is to subtract off or add any term that does not have dy dx in it. We want to move that to the other side. So now we have 18y dy dx equals negative 8x. Then we're going to divide both sides by 18y. So the derivative with respect to x, so the derivative of y with respect to x would be negative 8x divided by 18y. So this is the slope formula, the derivative of the function. Now we want to find the actual slope at this point 0, 2. So the slope at 0, 2, this is the x value and the y value of the point. So to find the slope, change in y with respect to change in x, we are going to plug in the 0 in place of x in the equation. So that's minus 8 times 0 divided by 18 times the y value of the point that we are given. So we're going to plug in the 2. So that gives us 0 over 36, which of course is just 0. So this is the slope of that x value. Alright, the next thing we're asked to do is find the equation. So if we know the slope at that given point, we know the slope is 0. If the slope at this given point is 0, then we can use our y minus y1 equals m times x minus x1. We can use our point slope formula in order to find the equation of that tangent line at the point 0, 2. So that would be y minus 2 is equal to 0 times x minus 0. 0 times anything else is just 0. So we have y minus 2 equals 0. And we will add 2 to both sides to find our equation. And of course, this is just a horizontal line, which makes sense because we know that horizontal lines have a slope of 0. And this is the equation of the tangent line. For our last example, we're asked to find the slope and the tangent line, the equation of the tangent line at the given point 2, 2 times the square root of 5. And here's our equation. So y squared, we want to take the derivative of y squared. That's a function raised to a power, so we will need to use the chain rule. So that would be 2 times the derivative of the inside, or times the inside function, as is, and then the derivative of the inside function, which we said was represented by dy dx. So the derivative of y is just dy dx. Minus, and of course the derivative of x squared is just 2x, equals, the derivative of 16 would just be 0. We're going to solve for dy dx. First thing we're going to do is bring over any term to the other side of the equation that does not contain dy dx. So that gives us a positive 2x now on the other side. Then we're going to divide by whatever's being multiplied times the front of dy dx. So we'll divide both sides by 2y. So the derivative of y with respect to x, or the slope formula, is 2x divided by 2y. And we can reduce this because 2 and 2 are common factors. We can cancel those out, and we're left with actually a reduced form of that would be x divided by y. And now we're asked to find the slope at a specific given point, 2 comma 2 square root of 5. So this is the x value of the point, and this is the y value of the point. So we're going to find our derivative. That slope formula, we're going to use that derivative. We're going to plug in place of x, we're going to plug in a 2. And in place of y, we're going to plug in 2 square root of 5. We're going to simplify this a little bit here. 2 and 2 cancel out, we're left with 1. So the slope that we're given is 1 divided by the square root of 5. So this is the slope at the point. And the equation of the tangent line, we're going to use the slope, that point slope formula, y minus y1 equals m times x minus x1. So that would be y minus, the y value of the point is 2 times the square root of 5. And the slope is 1 divided by the square root of 5. And then x minus the x value, which is 2. Now we're going to simplify a little bit. We'll multiply in our slope. So that would be 1 square root of 5 times x minus, think about this as a fraction, multiply across, that would be 1 times negative 2 is negative 2. Square root of 5 times 1 is the square root of 5. And the last thing we're going to do is we're going to add 2 square root of 5 to both sides of the equation. So we end up with y equals 1 divided by the square root of 5 times x. And then we need to combine these fractions together. So we want to give them a common denominator. And that common denominator would be the square root of 5. So I'm going to combine these. We're going to think about this as a fraction by putting it over 1. And then we're going to multiply top and the bottom of this fraction by the square root of 5. So we're going to multiply by the square root of 5 here and by the square root of 5 here. So that would be minus 2 square root of 5 plus the square root of 5 times the square root of 5 is just 5. And then 2 times 5 is 10 all over the square root of 5. And we're going to simplify that one more time. Now that those fractions actually have a common denominator, we're going to keep that common denominator and we're going to combine the numerators together. So minus 2 plus 10 would be a positive 8. So this would be the equation of the tangent line at that given point.